Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to be the part one of probably a three-part series I'm going to do on numerical integration. And what we're going to do here is we're going to take a look at the curve 4 minus x squared, and we're going to try to estimate the area bound in the first quadrant under that curve. So I've already went ahead and given ourselves a little picture of the sketch here. Now, when you're dealing with area problems, there's some language that goes with it. You have what are called lower bounds and upper bounds. It's pretty standard calculus language to let little a here represent the lower bound. So in this case, the lower bound here is going to be 0. And b, pretty standard notation for upper bounds. This curve right here, the intercept is at this point, goes through the point 2, 0. So our upper bound in this example is going to be 2. When you're dealing with numerical integration, usually the first thing you decide is how many pieces you're going to break the problem up into. So what I'm going to do here is I'm going to choose to break this up into n equals 4 pieces. Now, typically you would do quite a few more points than that, but I'm going to use 4 here just because this is just meant to be an introductory video to give us the flavor here of how numerical integration is done. Now, the next thing is you have to decide how we're going to break this thing up. And what I'm going to do is I'm going to break it up into rectangles. But there are different ways in which we can do that. Here's one possibility here. Perhaps I break this up into 4 rectangles that look maybe something like this. And that last one here actually wouldn't have any height to it. You'll notice that there's areas here, here, and here that are missing. So if I go ahead and work with this method, what's going to happen is I'm going to get an answer that's a little too small. Every time I talk about this approach, I think about Goldilocks and the 3 bears here. But if I calculated the areas of these 3 rectangles, I'm going to get a number that's not quite big enough. Another possibility here is perhaps I orient my rectangles like this. Now, if we do something like this, what you'll notice is now we're going to be including areas here, 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 and here that are not actually under the curve. So I'm going to get an answer that's a little too big. So what we want is something kind of in between here. So what I'm going to do, I am going to orient my rectangles so that the midpoint of the rectangle goes through the curve, maybe something like this. 1, 2, 3, 4. In textbooks, this is sometimes called the midpoint rule. I like to call it the Goldilocks rule here because now I'm going to get an answer that hopefully is a little bit better. You'll notice that I could basically cut this area out here that was included in the calculation and glue it here and get kind of a rough approximation to the area under the curve. Same thing here. Notice that if I kind of cut this, I can glue it right there and get something that's pretty close. Same thing here and same thing here. So this method should give us a pretty good method to estimate the area bound under this curve. Now, I'm going to give these rectangles names now. I'm going to call this one the first one, second one, third one, and fourth one. So I have now introduced really a new variable into this problem, this 1, 2, 3, 4, 5. This is what's called a dummy variable or an index variable here. And I'm going to assign the letter I to that variable here. So in this example, I can be a 1, 2, 3, or a 4. In general, I will run from 1 to n, whatever you choose n to be. To calculate the areas, I'm going to need a couple things. One, we're going to need the width of these rectangles, right? So in the language of math, that's what we would typically call a delta x. And you can usually get delta x by taking b minus a over n. That's your upper bound minus your lower bound, divide by how many rectangles. That's pretty simple calculation in this case here. Let's see, this was the point 2, 0. And I'm dividing it into 4 pieces. So this is going to be 2 over 4, which is 0.5. This will vary case by case. And you'll notice that the larger the value for n you choose, the smaller your delta x will be. Right? And I'll talk a little bit later in the video about your approximation and how to make it better. Right? Now, to calculate the length of, the area of that first rectangle, that's this stuff, what we need is its height. Now, it's very important to realize the height of that rectangle is the function value applied at that location. I'm going to call that value x1 here. That's the x value I need to get this height right there for that rectangle. Now you'll notice that that value, from here to here is delta x. So that value is halfway there. So that value is 0.25. I'm just going to write that down and move on. The next value I'm going to need is here, and then here, and then here. So this guy right here is the 0.25 plus a rectangle width. That's going to add another delta x there. So that's going to be 0.75. I'll just put this right here. So x2, 0.75. The third one I need is the x value at the center of this rectangle, again, for calculating the height of that rectangle. And again, we have to add another 0.5. And now we're at, let's see, 1.25. The fourth x value I'm going to need is right here at the center of the fourth rectangle. Again, we're going to need that value to calculate this height. And that one we're going to get by adding another 0.5 to our previous one, and that's going to be 1.75. Right? So these values are the appropriate x values to calculate the height of each rectangle. I'm going to draw those in green. These are the x values at these locations. And we need them to calculate these heights, this one, this one, this one, and this one. Once we have these heights, the area is just the area of a rectangle, length times width. So I'm going to go ahead and write this out. So A1 here, which is going to be the area of the first rectangle, that's this stuff, is equal to f of x1 times the width of this rectangle, delta x. So I'm just going to write this out. In this function here, we have 4 minus x squared. So that's going to be 4 minus 0.25 squared times delta x, which is 0.5. And I've already calculated that off to the side here so I didn't have to stop and do this. And I got about 1.97 out of that. Now I'm just going to write these down to 3 sig figs. If I was doing more numbers of rectangles, a higher value for n, I would record more significant figures. But again, this video, the intention is just kind of get the flavor of numerical integration and how it works. So 3 sig figs will be fine for this example. All right, area 2, that's going to be this area. And we're going to get that by taking our function 4 minus, and then apply to this x value, 4 minus 0.75 squared, and again times 0.5. Probably should have that in parentheses, both of them. And if we go ahead and run a value here, I get 1.72 out of that. Area 3, that's this stuff, we're going to get by the function value applied right there. So that's going to be 4 minus 1.25 squared times 0.5. And again, that's length times width. I get 1.22 out of that. Area 4, that's this guy right here. We're going to need the function value, 4 minus, right, applied here, 4 minus 1.75 squared, right, times the width of the rectangle, 0.5. That's going to give us 0.469. And now what I'm going to do is I'm just going to sum these all up. The total area we're going to get by summing up from I equals 1 to n. Now in this case it would be from 1 to 4 of all these a sub i's. And that's going to equal this number plus this number plus this number plus this number. And when I ran that, I got 5.38, give or take, approximating it to 3 significant figures. About 5.38, I'll just put square units there for the area. All right, so what we've done here is we've broken this curve up into pieces. We've approximated the area of each piece using a rectangle, using what I call the Goldilocks method here, where the rectangle goes, the function goes right through the center of the rectangle. We've calculated the appropriate x values at the center of each rectangle. And those x values allowed us to calculate the area of each rectangle by taking the length, which is given by the function value in this example, times the width, delta x. We add those all up, we get 5.38. Now I'd like to point something out here. If we actually did this via standard methods of calculus, that area would equal integral 0 to 2 of f of x dx. I'll just put f dx here, kind of shorthand it. And this is a pretty easy function to anti-differentiate. That's going to be 4x minus x to the third over 3 evaluated from 0 to 2. And if we run a value on that, what did I get here when I tried that? I got like 5.33 out of that. And a few more decimals here, just looking to 3 sig figs. So you notice the first 2 significant figures didn't change. If I actually rounded both answers to 2 significant figures, they're both 5.3. both answers rounded to 2 sig figs. Now, of course, this method gives an exact value. I could carry this out as far as I want, but I'd like to point out here that we got it correct to 2 sig figs using only 4 rectangles. Had I done, say, 10 rectangles, this value here would probably be good to that 3rd sig fig, probably even better. I find that 10 rectangles normally will give you less than 1% error on most problems. So this video is just meant to be a kind of an introduction into numerical integration. I'm going to make more examples to demonstrate these methods and how you'd use a computer. I like to use Microsoft Excel to do the calculations. I kept that out of here because I just wanted to keep this one simple. The highlights, though, are you break the curve up into pieces. You typically approximate the area with rectangles. You can also use trapezoids, and I'll make another video here about the trapezoid method. You calculate the width of each rectangle, the appropriate x values you need, calculate the area of each rectangle, add up all your results. I hope this video helps kind of demonstrate how the numerical methods basically work. Have a great day.